In this video, we're going to go through calculating the equilibrium constant. So let's begin by reviewing what is equilibrium. So remember, in equilibrium, the rates of the forward reaction are going to be equal to the rate of the reverse reaction. So products and reactants are being formed at the same rate. So the equilibrium constant expresses the ratio of product concentrations to reactant concentrations when we achieve equilibrium. The purpose of the constant is to help determine the extent of a reaction at a given temperature. We have two versions of the constant. We have Kc, which is used for reactions in solution. So when you see molarity, we're going to be using Kc. And then Kp is involved when we have gases. So when you see partial pressures or units of atmospheres, we're going to be using Kp. So this is the general formula for Kc. Again, Kc is when we have molarity. So all of our coefficients are represented in this general form with lowercase letters. Those now become exponents when we write out our equation, and it's always products over reactants. Okay, so you take the concentration of each product, and then any coefficient becomes an exponent over the reactants. Kp takes a similar form. However, when we write them out, it's going to be capital P and then lowercase, or not lowercase, but subscript for the concentration. Well, I'm sorry, the partial pressure will be a subscript here. And then just like before, the coefficients become exponents in our formula for Kp. Okay, so we're going to use Kp when we have partial pressures or units of atmospheres. Now Kp and Kc are related by this equation right here. So Kp is going to be equal to Kc times RT, and we raise that to delta N, which is going to be the moles of gaseous products minus the moles of gaseous reactants. All right, so let's dig into a problem that involves one of our equilibrium constants. So we have this reaction, and it gives us our equilibrium concentrations, and it's asking us to find Kc. So we're going to set this up. We're going to put our reactants over our products. So here we're going to have NH3 over our reactants. So we have N2 and H2. And then any coefficient becomes an exponent. So for NH3, we have this 2, and for H2, we have this 3. So that's how we set it up. The question actually gives us concentrations. So we're going to go ahead and we're going to plug those in. Okay. And then it's just a matter of putting this into our calculator. When we do that, we get an answer of 0.74. And our equilibrium constant does not have units. So that's all we would need for this question here. All right, let's do one that has partial pressures now. So just like the previous example, we're going to set this up, products over reactants. So I have SO3. I have SO2. And I have O2. Any coefficient becomes an exponent. So we have this half out in front here. So now it's just a matter of plugging in our numbers. So for SO3, we have 1.2. For SO2, we have 0.6. And for O2, we have 0.4. And of course, we're going to raise that to the power of 1/2. And if we plug this into our calculator, we get 3.2 as our answer. And again, this is going to be unitless because we are finding our equilibrium constant. Okay, so we can use this to find concentrations if we know our equilibrium constant. So here we know the value of our equilibrium constant, and it's asking us to find a concentration. So if we set this up, products over reactants, we are going to have Kc equals, we're going to have the concentration of our acid up here squared because there's a 2 over our reactants, so we have H2, and then we have I2. Okay. So when we do this, let's go ahead and plug in our numbers. So we've got 50.2. That is our equilibrium constant. We're solving for HI, so I'm just going to write that out here. And then let's plug in our denominator. So we have 0.25 for both of these. Okay, so I can actually simplify my denominator. So if I multiply these two numbers, I get 0.0625. And let's divide that over. So if we divide it over, we're also going to need to, in order to get rid of that 2, we're going to need to take the square root. So HI is going to be equal to the square root of whatever we get when we do 50.2 divided by, times 0.0625. Okay, and again, we're taking the square root because we have this 2 up here. Okay, so if I do that, I get 3.14 on the inside. If I take the square root of that, I get an answer of 1.77 or 1.8 as my answer here. So we're not just finding the equilibrium constant, we can use this setup to find individual concentrations, or in the case of gases, we could use it to find individual pressures.